Good morning, everyone. My name is John Pelletier, and I'm a project engineer with Jacobs. Today, I'll be presenting a recently completed project at the Manchester-Boston Regional Airport, the Runway Incursion Mitigation Project to reconfigure Taxiways P and U. I'd like to start by providing some background on the FAA's Runway Incursion Mitigation Program, which was the basis of this project. The definition of a runway incursion is any occurrence at an aerodrome involving the incorrect presence of an aircraft, vehicle, or person on the protected area of a surface designated for landing and takeoff of aircraft. The FAA has determined that airfield geometry is a primary contributing factor for runway incursions. Runway incursion data from 2007 to 2013 was used to develop an inventory of locations that might contribute to a runway incursion, otherwise known as hotspots. The overall goal of the RIM program is to identify, prioritize, and develop strategies to assist airports in mitigating risk at these locations. Some of the key risk factors for runway incursions are unclear taxiway markings, airport signage, and runway and taxiway layout, which is the most complex factor when it comes to mitigation. But it is certainly critical that it is addressed. I certainly wouldn't want to be in that Cessna. There were two hotspots at Manchester that were part of the FAA's inventory. Hotspot number 1 at the intersection of Taxiway Hotel and runway 17, and hotspot number 2 at the intersection of Taxiways Papa and Uniform at runway 35. This project will address hotspot number 2. The issue at hotspot number 2 is that aircraft are unable to hold short of the runway at a 90-degree angle and therefore do not have a clear line of sight in both directions of the runway. In this presentation, I'm going to highlight some of the work items that were involved in mitigating the runway incursion risk at Manchester. So for the primary work items, I'm going to discuss realignment of the taxiways, realignment of the vehicle service road, demolition and reconstruction of the MSC retaining wall, relocation of the high voltage duct bank that runs below the airport, along with some other work items, including reconstruction of the stormwater pond and construction of some infiltration chambers, a closed drainage system, a secondary de-icing pad, and miscellaneous airfield lighting, signage, and markings. In this sketch, you can see the proposed taxiway and service road pavement, represented by the gray hatching, overlaid on the existing taxiway and service road. The turn onto the renamed taxiways Alpha 1 and Alpha 2 has been pushed out from the runway to allow aircraft to hold short at a 90-degree angle, and also to ensure that when they do come to a stop, the nose wheel can be straight. Here you can see the final proposed layouts of taxiways Alpha 1 and Alpha 2, along with the new hold position markings. As you can see, the taxiway Alpha, which is up on this portion here, has been pushed back away from runway 35, which allows, like I said, the aircraft to come to a stop at the hold position marking at a 90-degree angle to the runway. This configuration also allows for an aircraft that's queuing on Alpha 2 to be safely bypassed by an aircraft taxiing on Alpha up to Alpha 1 on this side. To design the taxiway pavement, we use software developed by the FAA called Firefield. Firefield utilizes the California Bearing Ratio, or CBR, values of the subgrade material, as well as aircraft traffic data to provide a pavement section with a minimum 20-year service life. As you can see here in the figure on the right, this is a snapshot from Firefield. The top two surfaces are the asphalt surfaces, P401 and P403, followed by the P209 crushed aggregate base course, and then below that is the P154 uncrushed aggregate sub-base course, and then the hatched band at the bottom is the subgrade material with the associated CBR. Now, this slide here shows the actual traffic data that was utilized in developing the pavement section for this project. Just a summary of the heavier aircraft and also aircraft with a higher number of annual departures. For this purpose, a lot of the GA type Cessna aircraft are not accounted for, as obviously they don't have as much of an impact on the pavement as some of the larger commercial airlines such as the B757 and 737 down here at number 9 and 10, 175,000 pounds up to 273,000 pounds, or the freight aircraft, the 767, which can go up to 451,000 pounds of the takeoff weight. Here you can see a typical taxiway section. We ended up at 9 inches of asphalt on top of 6 inches of crushed aggregate and 18 inches of sub-base course, which was bumped up from what Firefield recommended at 5 inches, so that we were able to achieve a partial frost protection depth, which we could do with the inclusion of the underdrain system that is tied into our drainage system. So moving on to some of our secondary work items, the airport determined that there was a need for a secondary de-icing location to handle high queue times and peak traffic during inclement weather. Typically the aircraft would be de-iced on the ramp, but with this location being fairly remote from either the cargo ramp or the terminal apron, it's important to have a secondary backup location to de-ice any aircraft that are either held up in a taxi queue or in this case, holding short for extended duration, waiting to be clear for takeoff. So what would happen is the aircraft would taxi up taxiway Alpha and stop in this location here and be de-iced. These 3 catch basins on the left side, along with this single basin in the center here, would capture the glycol, and in a de-icing event, the valve would be actuated to allow the glycol into the 300-gallon holding tank, which would then need to be pumped out after the de-icing event. Otherwise, the valves would just be open to allow storm water to flow through into the storm drain. On this slide, we have the alignment and profile of the new mechanically stabilized earth, or MSE wall. This wall was constructed to accommodate the realignment of the taxiway and service road. The existing taxiway did have an MSE wall prior to construction that needed to be demolished to accommodate the new taxiway location. Some key statistics on the wall: it's about 20 feet maximum height at its highest point. It consists of 12,500 square feet of MSE wall panels, and it's about 860 feet in length. And here we have the high voltage duct bank relocation. There was an existing high voltage duct bank running underneath the airport, providing service to Southeast Londonderry. As you can see in the sketch on the left, the existing duct bank runs directly below the proposed taxiway alignment. So that would need to be relocated prior to construction of the new taxiway. As you can probably guess, there was a fair amount of coordination needed to transition power to the new duct bank, since we could not interrupt service during peak heating or cooling seasons. In order to achieve this, a portion of the service road was demolished in the fall of 2018 so that we could cut power over prior to the winter, which allowed us to start the construction of the taxiway right away in the spring of 2019. The project did require DES alteration of terrain permitting, since it was set to disturb about 1.5 million square feet. In order to handle the increased runoff created by the added impervious area, the existing retention pond, in this area here, was modified to store an additional 110,000 cubic feet of water to reduce peak discharges. We also utilized StormTech chambers as a water quality BMP. You'll see a lot of underground infiltration and detention practices on airports, since the FAA does not allow ponded water to be held for longer than 48 hours. Anything after 48 hours, the FAA considers that to be a wildlife attractant. And so this, the StormTech chambers, you can see in the cross section here, the SC-740 chambers we used. There was a total of 210 of those. And that's actually directly adjacent to the pond, so that those chambers will capture the initial runoff prior to bypassing to the pond. And the pond ultimately feeds into the little Cohas Brook that flows below the airport. And one last thing I wanted to touch on that was somewhat special to this project and airport projects in general, over and above the typical phasing of airport projects that we have to handle is anytime we're working adjacent to a runway, we have to include contingencies for emergency reopenings of that runway. In our case, we did have an Air Force One landing in August of 2019. So in order to accommodate that, the contractor spent a couple of weeks regrading the safety areas to get those back up to standard, filling excavations, and in general buttoning up all the work adjacent to the runway so that the runway would be safe for landing. One night in and out, then the contractor returned back to work, a couple more weeks worth of work to undo the temporary work that was done. So a total of 4 to 5 weeks worth of work to accommodate an emergency reopening of the runway. And here you can see some aerial photographs of the completed project. Taxiway P&U project completed in the fall of 2019. On the bottom of the photo on the left. To the north, there is some follow-on reconstruction of Taxiway Alpha, Taxiway Foxtrot, and the intersection of Taxiway Alpha and Taxiway Echo. Most of that was drainage work and, like I said, taxiway reconstruction, and also taxiway geometry updates to bring those up to the new FAA standard. The total construction cost for the P&U project was about $9.6 million. If you include the follow-on reconstruction portions, it came out to about $14.3 million. The overall duration of the taxiway P&U project was 196 days, so about 6.5 months, and that includes a winter stoppage that was in there. I'd like to just take a minute to acknowledge some of the key players that really made this project happen. John Kirkendall of FAA New England, Ted Kitchens, Manchester Airport Director, Tom Malafront, Manchester Airport Deputy Director, and Carlton Braley, Manchester Airport Assistant Director, along with obviously the guys that made it happen, R.S. Audley, our prime contractor, and Jacobs Engineering Group. We are the engineer of record. I'm not sure if we're going to have time for live questions after this, but if you have any specific questions, please feel free to email me. I've included my email address at the bottom of the slide. Thank you.